And I find the topic of curiosity extremely fascinating. I want to preface this by saying that I'm not really making any very grandiose claims about curiosity, but I think we can probably all agree that curiosity is multifaceted, and what I'm going to talk about is really just one facet, which is novelty preferences in humans. And what I want to try to convince you of today is that those novelty preferences are in large part inductive in nature. Okay. So I want to start with what I call the puzzle of novelty. So what's puzzling about novelty? Well, there's a very formidable canon of research that suggests that that humans and other animals are neophilic. They are attracted to novelty. On the other hand, there's an equally formidable canon of research that suggests that animals and humans are neophobic. They're actually repelled by novelty. And it's a little bit mind-boggling how to reconcile these. There's this huge numbers of papers going back 100 years. And there are many subtleties. So there are differences between different kinds of animals, between tame and feral animals. Depends on the degree of novelty, the familiarity of the context, and various other things. And I'll try to touch upon some of these towards the end, but I'm not going to be able to attend to all of these different subtleties. I'll just talk about a new theoretical framework that tries to reconcile some of these issues. And this has important theoretical implications for the kinds of reinforcement learning models that, for example, Michael was just talking about, particularly where the role of novelty in reinforcement learning models has often played particular roles in terms of either balancing exploration and exploitation, or in terms of gathering information about a hidden state, as Michael talked about. Another important question here has to do with the neural basis of novelty preferences, and in particular how this fits into reinforcement learning theories of the basal ganglia and the dopaminergic system. And I'll come back to that in a few slides. So, okay, so here are a few examples of neophilia. For example, animals who learn to associate a place with a novel object will prefer that place over a different place that wasn't paired with novelty before. And in fact, this novelty preference can be so strong in some cases that it can even compete with cocaine reward. Now, on the other hand, here's an example of neophobia, where an animal is placed in this environment where initially this food basket is baited. And then after day 3, the food basket is no longer baited, and now this new tin is placed in the environment, and the tin is baited. And if you do this experiment with wild rats, they'll actually go for 3 days without eating anything before they venture to try to sample food from this novel tin. And interestingly, tame rats don't show this neophobia. Tame rats will will immediately go and eat from the food tin. And at the end, I'll offer a speculation about why that might be. Okay, so coming back to dopamine, many of you are probably familiar with this idea that the sort of modern computational synthesis of theories about dopamine holds that phasic firing of dopaminergic neurons represents some kind of reward prediction error. But actually, very soon after that hypothesis was proposed, various challenges to that hypothesis arose, and among the first was this observation that dopamine neurons fire in response to a novel stimulus, even when it doesn't have any obvious reward value. So how do you reconcile that with a reward prediction error? Well, oh yeah, and so one other point is that you can see the same kind of novelty response in the fMRI bold signal in the striatum in humans. So Sham Kakade and Peter Dan tried to reconcile this observation of novelty responses with traditional prediction error theory, and to do this they actually borrowed from some important ideas in machine learning, which holds that novelty is actually really important for encouraging exploration in environments when you're learning about them. And there's a venerable tradition of basically adding kind of a surrogate reward to unexplored states in order to encourage exploration of them. And this goes back to, for example, Braffen and Tannenholz's R-max algorithm, and the particular framework that Kakade and Dayan used was this notion of a shaping bonus, which is effectively an optimistic initialization of the state values. And they showed that this could explain why dopamine responds to novel stimuli. Now, there's a problem here, which is that so while shaping bonuses offer a nice explanation of dopamine responses to novelty, they're not in general adaptive from a reinforced learning perspective. And the reason is that in very poor environments, a new stimulus could actually be bad. It could be negative. You might not want to explore new things if you think that new things are good.
Poor environments is like
poor or aversive environment. So poor could mean that new things tend to be less good than the things that you already have. Yeah. Or it could be actually aversive. And in rich environments, it's unlikely actually that a new stimulus would be better than a stimulus that you already encountered. And shaping bonuses obviously also can account for why neophobia is sometimes observed. So what I'd like to do is try to lay out a different way of thinking about this. Not necessarily mutually exclusive with the shaping bonuses idea, but it sort of expands this idea. So what is actually the value of a novel stimulus or action? In order to generalize from your previous experience to some new stimulus, you have to have you have to have some internal model of the environment and of the stimulus values that allows you to generalize. So one way to rationalize this is to say that different stimuli in an environment tend to have similar values. And by formalizing this in a probabilistic manner, it gives you a principled way to generalize from experience with one set of stimuli to a new stimulus from that same environment. And I'm going to formalize this particularly by using a hierarchical probabilistic model where the stimulus values are all drawn from a common distribution. I'm going to call that the contextual prior. And then given this contextual prior, Bayes' rule tells you how to generalize from your previous experience to new experience. Okay, so to give you a few intuitions here, roughly speaking, the value of a novel stimulus is going to be close to the average reward of the other stimuli that you experienced in the same environment. And the parameters of the contextual prior, so this is essentially the mean and variance, so to speak, of that prior, will determine, will represent your abstract knowledge about the environment and determine how you're going to generalize to new stimuli. So here are some examples from the real world. You go to a restaurant. These are pictures from this restaurant Momofuku in New York, which is quite good. And I don't have to try everything on Momofuku's menu to know that that some new thing that I've never tried before is probably going to be good. On the other hand, if I go to some other, well, this is all subjective, so this doesn't look terribly appetizing to me. And if I've tried a number of these dishes at this particular establishment, I might make a different generalization that a new thing is going to be equally unappetizing. So I think that we do this kind of calculation in our heads quite frequently in everyday life. So how do we formalize this? So I'm going to talk about, I'm going to relate this to a specific experimental task that I'll introduce in a moment. And this is basically a version of the multi-armed bandit, but where the bandits are organized into a kind of contextual structure that I'll explain in a second. So the idea is that each arm of the bandit, they're K arms, and they yield a binary reward with some probability theta. And all of these thetas are drawn from some common distribution, which is a beta distribution in this case. And the beta distribution has two parameters. So one is the mean of the beta distribution. So I call that B, and I call that the inductive bias. And then there's this coupling parameter rho, which basically corresponds to the inverse variance. And so this shows you two examples of contextual priors with different parameters. So under weak coupling, there's going to be large variance between the reward probabilities across the arms of the bandit, whereas with strong coupling, they're going to be more tightly clustered around the inductive bias, B, the mean. And then, so you draw all of these reward probabilities, and then when you actually play the bandit, you're going to, in each trial, choose one of these arms and get some binary reward with that probability. Does that make sense to everybody so far? Okay. And it turns out that there's an interesting connection between this kind of hierarchical Bayesian model, which is just an abstract description of the ideal observer, and the Rescorla-Wagner model, which is just a mechanistic model of reinforcement learning. And it turns out that under certain assumptions, you can show that the values learned by Rescorla-Wagner are actually equivalent to their expectation under the posterior of this model. That is, the posterior mean of these latent reward probabilities. And so I'm not going to go through the math in detail, but I just want to give you a feel for this. So the Rescorla-Wagner model, you have some cached value for every arm of the bandit that you're updating based on the prediction error. So here's the prediction error. You observe reward at trial t, and you compare that to your expected reward, and you update it using this learning rate eta. And if we set the initial value to the inductive bias b, so that's the mean of this contextual prior. And we set the learning rate to be this monotonically declining function of the number of times that you chose a particular arm. Then you get then these values are equivalent to the posterior mean of the mean of the posterior over these over the arm reward probabilities. And you can see that this coupling parameter shows up in the denominator of the learning rate, and the intuition here, which I illustrate in this slide, is that when you have a very strong coupling parameter, then you expect more of the arms to be closer to the mean of that distribution, and so you're effectively going to be learning less. You should learn less about the arms because you're going to hew more closely to your prior. And so that's shown here. This is the learning rate as a function of the number of times you've tried a particular arm, and the learning rate is lower under strong coupling. Okay, so now I'm going to talk about some behavioral experiments that I've done with humans. And the idea here is to try to test the predictions of this inductive generalization framework and compare it across, compare it to a few different other models of reinforcement learning. In particular, the idea of using a shaping bonus or just a naive initialization where you initialize all the values to 0. Okay, so the cover story here, which I stole from Todd Garekis partly, is that subjects are playing this interplanetary farmer game where they're traveling to other planets and they're going to harvest crops on different planets. And what we do is we present to them different crop options that they can harvest, and then they get some probabilistic feedback about whether that crop was successful or not. And importantly, and one other aspect of this is that so in the first experiment, they're actually getting to choose between a particular crop and a reference crop, which always yields a success with probability 0.5. And the important manipulation here is that some planets are fertile in the sense that many crops yield reward, and some planets are infertile in the sense that most crops don't yield any reward. And there's a large amount of variability across the different planets that subjects encounter. So if subjects are making this sort of abstract inference about the contextual prior, their choices should be modulated by previous reward history on each planet. And that's exactly what we showed. So what I'm plotting here is on the x-axis is the average reward they've encountered so far on a particular planet across all the different crops that they've tried. And on the y-axis is the probability that they choose a novel option. Oh, I forgot to mention an important thing, which is that every 6 to 12 trials, a new crop option appears on the planet, and they get to decide whether or not they want to choose this novel crop option or the reference crop. So what you can see is that the probability that they're going to choose the novel crop option monotonically increases as a function of the average reward on that planet so far. So that's this black line here. This is the empirical distribution. And this red line here is the shaping bonus model, where we just fit a fixed initial value of the value function to each individual participant. So you can see that it's flat across average rewards because it's not an adaptive novelty bonus, whereas the naive model always initializes to 0 and sorry, the naive model will always choose with a probability of 0.5 the novel crop. But you can see that the shaping, the Bayesian model, which is this blue line, also exhibits this monotonically increasing novelty preference as a function of average reward. Okay. And we've done some formal model comparison using cross-validation to show that the Bayesian model is indeed a better quantitative explanation of the trial-by-trial choice behavior of our subjects than either the shaping or naive model. The second experiment is much like the first experiment, but here we're going to show one crop at a time, and subjects are going to use a slider to rate their gut feeling about whether or not that crop is going to be successful. And again, every 6 to 12 trials, we're going to swap in another crop. And what we find again is that this reward prediction is monotonically increasing as a function. The novel choice, the reward prediction for the novel choice is monotonically increasing as a function of the average reward on the planet, consistent with the Bayesian model, but inconsistent with the shaping model or the naive model, which in this case is just at 0, so I'm not showing it. Yeah, Laura.
In both cases, it's consistent with what people are more optimistic.
Yeah, that's an important point.
Is that because they're getting information as well as reward? Or
I'm not sure. So it could be that basically this inductive bias is getting superimposed on some kind of baseline novelty bias, or it could be something like they actually have some information-based exploration bonus. I'm not sure. Yeah, Michael. Yeah.
So even actually, aside from the information bonus,
yeah,
it's clear why the Bayes model does better than either the novelty,
yeah,
the naive one,
yeah,
or the shaping one.
Yeah.
How much of the structure of the Bayesian part is necessary? So if you had an RL model that learnt the probability, the overall value across an environment, and just does it according to naive reward prediction error, but it just uses that to set the bonus for that.
Yeah. Well, part of my point of the previous slide is that that's actually what the Bayesian model implies. So that you can implement this Bayesian model doing something that's very close to what you're describing. You just have to make certain assumptions about the learning rate, and it turns into something that's equivalent to directly estimating the posterior.
Right. And the question is whether those assumptions about the learning rate that make it Bayesian are actually better or worse fit, because in both cases you're capturing the general profile but missing some of the details and whether
right.
I'm wondering whether.
Yeah, no, that's a good question. I don't have any data that speak directly to that. I mean, in principle, one could just implement that model and fit it to the data. Yeah, yeah, that's a good question. It might be worth doing. Yeah, well, yeah.
How do you go from attributing value to choice? Is it just choose the option that gives you?
Oh yeah, sorry, I didn't mention that. So I'm using just a very standard logistic sigmoid choice probability. So you're taking.
So it's a stochastic rule of some kind.
Exactly. Yeah, that's right. Yeah, and that's right. In these experiments, they just literally report their value prediction, or that's what we're assuming they're doing. But in the choice experiments, they're they're passing the values through a logistic sigmoid. Okay. And again, the model comparison supports this Bayesian account over the alternative models. The last experiment that I'm going to talk about looks at a form of retrospective evaluation. So the idea is that if you experience a bad crop early on a planet, and then all the crops that you experience after that one bad crop are really good, and I show you the bad crop again at the end of the planet, am I going to shift my preference for the bad crop such that I'm going to be more likely to choose this bad crop again, having seen these other good crops on that planet? So the idea is essentially that are you regularizing your estimates of individual crops based on the experience with all the other crops on the planet? And we can do this we can do the same thing by giving you a good crop at the beginning of your experience on the planet, and then showing you a bunch of bad crops, and then asking you about that initially good crop again. In that case, you should push your choices. You should push your preference down, and that's exactly what we saw. So positive discrepancies here. The discrepancy here represents the difference between your preference at the end of the block versus the beginning of the block. And when you start with a good crop and you then experience a bunch of bad crops, that pushes your value down. And the opposite happens if you start with a bad crop and you experience a bunch of good crops. And this qualitative pattern can be captured by the model as well. Okay, so what I've argued here is that human behavior on this simple sort of bandit task can be captured by a Bayesian model of inductive generalization that expresses one's belief about novel stimuli in terms of abstract inferences about this contextual prior. So fundamentally, the novelty responses aren't some fixed bonus for new things, but actually novelty responses are adaptive. And my hope is that this kind of framework can be illuminating about the contradictions that exist in the Neophobia, Neophilia literature that potentially could explain why sometimes animals, under some circumstances and some kinds of animals, prefer novel things and some prefer familiar things. And just to give one blatant speculation about this, so remember I showed you that wild rats will completely refuse to try a novel food tin after it's introduced, and not to the point of not eating for 3 whole days, whereas tame rats will gleefully go and eat from that tin. Well, perhaps that has to do with the previous experience of tame versus wild rats, that wild rats are used to having to contend with some kind of like fatal novelties of the real world. So new things actually could very often be very bad for wild rats, whereas for tame rats, they're getting fed on a regular basis. They have no reason to think that some new thing is going to kill them all of a sudden. So that's just a speculation, but that's the kind of reasoning that I think could be useful in reconciling the contradictions of that literature. And I want to thank my collaborators in this work, particularly Yael Niv at Princeton, who's my PhD advisor, and Alex Tank, who is a very helpful research assistant. And thank you for listening.
Questions? So just to follow up on sort of a hybrid, I guess, in between the full Bayesian thing and a naive RL for learning novelty bonuses is the possibility that the world might be changing would be, I guess, an expanded Bayesian model that has some volatility instead of allowing the learning rate to just go down.
That's right, yeah.
Is it possible that might be explaining the discrepancy?
Would that explain it? So you're saying, so if the learning rate doesn't go down as steeply, could that explain why there's sort of a baseline shift upward of the novelty preferences?
I mean, I depends on how your task was administered and whether.
Right, yeah. I mean, that's an interesting idea. I don't have an immediate intuition for if that would be true or not. But that's certainly something that would fall within this formal framework that you could do. One thing that I wasn't so explicit about here was how actually the model does learns about the inductive bias itself. So what the math that I showed you was for when the inductive bias and the coupling parameter are known, but in actuality, subjects don't know those parameters, so they have to learn it. Actually, we assume that subjects assume a fixed coupling parameter, but what they do to learn about the inductive bias is basically, since this is just a one-dimensional parameter that's between 0 and 1, we just discretize that space, and we assume that subjects are basically learning a hypothetical value function for every possible inductive bias, and then they're taking a weighted average of those value functions based on their belief about which value function. So in some ways it's like what you're doing with the latent context. So in this case, the latent context is actually this latent inductive bias. So it's actually not equivalent to simply learning an average reward and initializing there, but in practice it might make very similar predictions. Yeah. Yes?
If I understood that correctly, but it seems that you really, I mean, in this curve you have on the x-axis the average fertility of the planet.
Yeah.
Then you show that basically the probability of choosing a novel stimulus goes up with that, right?
Yeah.
But I mean, you could have examples where you have, on average, a very fertile planet, but the variance is very high, right?
Right.
So you shouldn't. So I wonder if how subjects would do in such tasks.
Yeah.
Because this really seems to assume that the variance is not too high.
Right.
You can just go with that variance.
Yeah, we didn't manipulate that in our studies, but that would be that would definitely be a relevant variable to manipulate in this. If we really wanted to make a strong argument about this Bayesian framework where we can explicitly represent these parameters in terms of a hierarchical model. Yeah, I agree.
So I didn't follow exactly the details of the model, but I think the question is related.
Yeah.
If there's a possibility of a deadly choice,
yes,
you shouldn't even explore, right?
That's right. Yeah. If you had a very strong, so I didn't. Also, these are all appetitive tasks, right? But you could do this with aversive stimuli, where yes, that's right. If you had an inductive bias that was strongly negative, then you would not want to explore according to this framework.
If you get a solution that is good enough, you just stop.
That's right. Yeah. Jackie?
So this seems to me to apply to the case of sort of mild novelty. Even the examples where you have a new exemplar, but it's really similar to what you've seen before. And so it belongs clearly to a context.
Right. I mean, we set it up explicitly that you're on a planet, you're getting crops that are,
Right. So you believe you're still on that planet. But what if you have something completely new, and you might think, oops, the context has changed.
Right. Well, actually, now you're getting closer to the scenario that Michael is talking about in some sense. And actually, this is something that I've studied a lot, where the context is actually a latent variable that you have to infer, where there's some discrete context or discrete latent cause that you have to infer, and that determines your generalization. Yeah. So that, and I think that's probably true in many real-world scenarios. And that we were just trying to simplify things where the context, right? But you could definitely do that. That would be a natural extension.
And probably we can imagine that the generalization mechanism that could apply to context themselves. Like you could probably have a generalization.
Absolutely.
That certain contexts have features that, in general, for them it's good to explore novel things.
Right.
And some other contexts have general features that you can predict that exploring novel things in this context is going to be.
Absolutely. Yeah. So and this is related to a whole line of research in machine learning on multitask learning, where you might learn about some tasks, and then you have to the tasks might be identified in some kind of parameter space, and you have to when you encounter a new task, you have to infer whether where that task falls in the task parameter space. So yeah, maybe. Yeah, Laura.
Especially tasks are unvalenced. Would you have so again it's purely just the information you're generalizing from context to context. Is there any?
Well, then this framework kind of starts to fall apart, because this is fundamentally a reinforcement learning model, and it's all about learning value. So there are ways to get around that, right? Like, and I think a number of people in this room thought about this question of like, maybe I need to change my value function in such a way that it has pure informational components, and in that case you would get you could get,
well, go ahead.
Yeah. In that case, you would get informational sort of inductive biases, informational novelty bonuses in some sense.
In that case, the more you can generalize, the less the value, right? So the less informative context is.
Yeah, the less informative, right.
I mean, you should explore if you can't generalize.
That's right. Yeah. So these are sort of two sides of the same coin. Yeah, it's a little bit confusing to think about, right? In some sense, you might be making an inductive generalization about your own your uncertainty about. You might use generalization in order to generalize how much you know or don't know. Exactly. Yeah.
Questions? No. We are time to coffee break. So.
All right. Thank you.
Thanks again.